Um, Hello, my name is Timur. I'm going to give the talk in English. I hope it's fine for everyone. If you don't understand me, just interrupt. Um, it's great to be here at C++ Russia. So thanks, Sergey, for inviting me here to speak here. So I work at Roli, which is a music technology company in London, doing software and hardware for music production. We also do Juice, which is a C++ cross-platform C++ framework for writing applications for desktop and mobile platforms. And we also organize the ADC, which is the Audio Developer Conference, which is the annual conference of the music and audio developer world. So this talk is called Readable Modern C++ version 2. The reason why it's called version 2 is because I gave a version of this talk 3 days ago at the C++ user group in St. Petersburg. And probably this version will be on YouTube somewhere at some point. And the first half of the talk was about general, sort of how to write general readable code. So things like naming, commenting, formatting, and things like that. And the feedback was basically, we know all this stuff already. These are all the basics. Don't talk about this stuff. Talk about more about modern C++. And I was really happy to hear that. So in the last couple of days, I reworked the talk. So there's going to be more modern C++ stuff in there. And I have to say one thing. So there was a problem with the projector here. So I can't actually use my notebook for the presentation, which means that I don't have my notes, and also there's a lot of animations on the slides that are not going to be working because now I have to use a PDF version. So some of the slides will be messed up. Really sorry for that because we couldn't get it to work with the video output on my MacBook. So I'm going to try to compensate for that by maybe explaining how it was supposed to be. So really, really sorry for that. It's a technical problem. So. So as I said, modern C++, there's actually one line of code in my talk that is not modern C++. And that's this line of code right there. That is a punch card. And that is not modern C++, and it's also not particularly readable either. The holes, actually, they do encode characters, so it all does make sense. And you don't even need the holes. At the top of the card, the actual line of code is also printed. I don't know if you can see this. But this is also not very readable either. There's a lot of short variable names, like one letter variable names, everything squeezed into one line of code. So it's really hard to figure out what this line of code does. This, however, is not a problem, I think, because this punch card is not intended to be read by people. This punch card is intended to be like your program is a stack of those punch cards, and then you feed them physically into the machine, right? So that's the purpose. It's not designed to be readable. However, fortunately, that's not what we're doing. We're writing C++, and I really like this quote. I unfortunately don't remember where this is from, but high-level languages like C++ are usually not written to communicate with compilers. They're usually written to communicate with people. And I think that's really important to remember that. A typical developer spends only about 20% of the time working, actually writing their own code, and maybe about 80% of the time looking at other people's code. You try to understand an algorithm, you're trying to find a bug, you're trying to figure out where your new code is going to fit in. That's a common problem with legacy code. So you're staring at other people's code. And the other thing is that over the lifetime of an application, at least 80%, and actually often more than 90% of the time and the money, they also don't go into writing the code, but they go into maintaining the code. And then, in many projects, people come and go, and people have different levels of knowledge of C++. So these are all reasons why I think it's really important to keep the code base readable by people. Now, how do we do that? And there's a lot of literature on the subject. Let me just point out one particular book, this one here. Who has read this book? That's great. I think that every developer should read this book, in my opinion. And for everyone who has not read this book, I can summarize this book in one slide. And that's actually the most important slide of the talk. I really think this is true. You know, code quality is measured in WTFs per minute, which that means good code should be readable. In fact, I think it should be as close as possible to plain English. Now, you know, how do we do that? There's several layers here. So first of all, you can have coding standards. Like in Juice, we have, I think, good coding standards. They're really great. They're online. You know, Google has famously, they have their coding guidelines online. I'm sure many other people, many other companies also have their internal coding guidelines. You know, this is stuff like white spaces, camel case, indentation, syntax. You know, if you have different syntaxes, which one do you choose? And you know, what features of C++ you use or not use? And this is really important. And I think everyone should have that. Then there's another layer, which is architecture. And this is stuff like design patterns, modularity, abstracting things away, you know, not sticking everything into one big class. If you're writing a library, it also means designing a clear interface, designing clear APIs. So all of this stuff. And then there is a much more generic, kind of basic notion of clean code. And this involves things like these things, basically. And we will keep coming back to these things during the talk. So, you know, do what people expect. You know, if you're solving a problem, use the least complicated and most commonly known solution. Express yourself in code, not in comments, by choosing good names for your variables and methods, and you know, avoid repetition, avoid redundancy. Try to type shorter code, less code, because less code is, you know, less bugs, less to read, less to understand, less to reason about. And, you know, scope, that things should be only in the scope where they're actually used, and locality, which basically means things like, you know, the person who reads your code shouldn't be scrolling too much and shouldn't be having to look up the function's definition to understand what it's doing, and things like that. Let me just quickly give you some two very basic examples. You know, if you have a simple code like this, you know, you have an if branch and an else branch, then technically the else is not needed. So I would not write that else, I would omit that. And actually by doing that, I'm adding more information. I'm saying, hey, you know, the first case is probably something like a special case, and then the second case, the second return is like the default. This is another example where, you know, people write functions like this, where you know, you have these flag arguments. It's doing something, and then you have these options. And then this immediately is a WTF per minute, because there's no way you can understand what it does without looking up the function. Now, people say, you know, we have IDEs, so you just hover with the mouse over the function, it's going to tell you what the arguments mean. And I don't think this argument really holds. Because, you know, first of all, many people like myself, they don't work in an environment where everyone uses the same IDE. And then also there will be always like this one person with just a text editor. And even if you can hover with the mouse over the code and it's going to tell you what the arguments mean, I still think that it would be better if you would write code imagining that you couldn't do that, because code should be readable independent of the tools that you use. So, you know, you could give names to those values, you could split them into multiple functions. You could write like a struct with like a settings struct and put those three settings in there. You know, whatever fits your architecture better. So yeah, this kind of stuff. So these are sort of like the generic principles. If I say what I mean if I say readable code. Now, how does this apply to C++? Okay, I'm sorry, I'm also a bit confused here because I have the clicker for this and then I have the arrow for some notes here, so sorry for that again. So the first observation here is that for some reason it seems to me that C++ is an inherently difficult to read language. Let me show you what I mean. Again, very simple example. You have a string. That could be an example maybe in a job interview for C++ developer. Replace basically one substring with another substring. And this is the kind of stuff that I think should, you shouldn't be even thinking about this stuff. This is so basic, it should take you 5 seconds to do that, right? So let's all think for 5 seconds about how to do that. Very nice. So if you don't have boost, then it turns out, well, maybe you don't know in 5 seconds, so you're going to go to Stack Overflow. So let's see what Stack Overflow says. Turns out, yes, it's not there in C++, you have to implement it yourself. That's the top answer. Okay, that's nice. Okay, that one actually uses an in-out parameter, maybe as a string, maybe that's not what you want. So here's an option that returns a modified string. I like the second one. It says if you need performance, here's an optimized version. There's the third answer says, I believe this could work. Const char instead of string. These days you could probably also use a string view. In C++ 11 we have regex, so here's the solution with regex. That's cool, right? Regex, always good. And of course we have templates, so here's a templatized version. Yeah. Now, I don't have that problem personally because I use Juice, and in Juice we have a string class, like I'm sure many other frameworks do, and there it's a one-liner, and someone said Boost has this too. So also in Boost it's a one-liner. And not everyone is allowed to use Boost or uses Boost in their job. So I think this kind of stuff should really be in the standard. Let me give you another example. Let's say you have a vector of items and you want to remove all the invalid items. So this is the way in C++ how you would do that. And I think it's really ugly. It's so ugly, actually, I don't even know how to like indent this properly. It's also confusing because remove doesn't actually remove anything. It just shuffles some stuff to the end. And also, that's like remove is not a function name that I would necessarily choose in this case. It's not an easy thing to remember either. And then there's this whole thing about algorithmic complexity where, this is linear. But if you don't write it like that, then probably it's going to be not linear. And it contains a lot of stuff that has nothing to do with what we're doing, like all the red stuff here. It's just boilerplate, right? It doesn't tell us anything. So the code that we actually want to write is sort of like the English that tells us what happens, is the stuff in between. Like items remove if item is not valid. So that's the kind of code that I want to write. Now again in Juice we can write this shorter, but this is not a talk about Juice. It's a talk about C++. So actually in C++, there is a proposal for the standard. It's in a technical specification, which is called Library Fundamentals TS, second version to that. And that's really nice. So that's a proposal for a function like this, which takes a non-const reference to a vector. There's overloads for the other containers as well. And then it takes a predicate and it does the erase remove thing for you, right? So that's really cool. There's still a little bit of boilerplate. Here again, the red stuff. So sorry, again, the sort of like the red stuff, for example, it's supposed to appear, but none of the animations on the slides work. Sorry for that. So anyway, this is currently not a part of the language yet, but it's going to be. And this is exactly the kind of stuff that keeps me really excited, because I think C++ is actually getting better and better and more readable. Now as C++ evolves, we have all these different stages. We have C++ 11 standard, we have the C++ 14 standard, which is going to be most of the code in this talk. Then there's the upcoming C++ 17 standard. I'm going to talk about some about that stuff as well. And then there's these technical specifications, which are essentially like feature branches that have not been merged back in yet. Let's see. So yeah, we have all these features. Now, one question is, can you actually use them? You know, it depends on what compiler you use, what version of the compiler you use, what kind of what access do you have to those features or to these different sets of features. So that's a question that you need to ask yourself. But the questions that I'm asking myself also is, should I use these new features, right? And that again depends on what you're doing and what kind of code you write. But I'm always trying to ask those questions. You know, if I have a new feature, does it add any information? Does it reduce redundancy and repetition? Does it make the code safer? Does it replace something else that is less readable and more ugly? And most importantly, will everyone in my team understand the code? And if you know, a new feature is not going to tick, you know, at least 3 or maybe 4 of those boxes, then, you know, I'm not going to use this in production code, no matter how cool and elegant it is. Let's talk about some of these features. constexpr. So constexpr is great. It's great for compile time programming. Constexpr functions let you write code that otherwise would be some, you know, really ugly template metaprogramming stuff that's hard to read, especially if you're not experienced with template metaprogramming. So constexpr is great. But that's a whole task in its a talk in itself. So let me here just mention a much more basic use of constexpr to achieve more readable code when we talk about these, you know, basics of clean code. And one thing that I always flag in code reviews is if people use kind of magic numbers, you know, like reserve 4K of memory. Why 4K? Why not 8K? Some people write a comment, you know. I think if you express your if you express what you're trying to do in comments, it's better to express it in code. So you know, for a long time people used macros for this kind of stuff. I don't actually think macros are code. I think macros are some like text replacement thing on top of the language. I don't really like them. But yeah, if you have constexpr, you can use it for compile time constants. You know, and that's much nicer. That achieves the same thing, but actually the compiler sees the name and also the compiler sees the type of the thing. So it can make some additional checks. It's much safer. So that's great. There's one problem with constexpr that you know, if you start using this kind of stuff and you get more into it, I've seen a few times people running into problems if you have if you start to put this kind of stuff in a struct, for example, and then there you can have a problem where if you then use this struct, this constant in a struct, if you use it in another file, you might get a linker error like this, which you wouldn't get with a macro. So the reason for this linker error is that stdmin. So what we're doing here is we're using stdmin, which takes a reference to its argument, right? So it takes a reference to the constexpr. And this is what in C++ we call ODR use. So if you take a reference to something, or if you take the address to something, and at that point, the compiler needs to actually create that symbol. And then this whole thing about constexpr sort of breaks down. And then the normal rules apply where if you have a static member, you have to define it in a header file and declare it in a header file, define it in a CBP file, and so on. If you're not doing that, you're getting these linker errors. So that's not nice. But you know, there's one right way to fix this, and there's a bad way and a good way to fix this. Now the bad way to fix this is to do it like this. So instead of taking the reference to the constexpr, we're creating a temporary and we're taking a reference to that, and then that's going to compile. But then this is just again boilerplate that is just confusing. You know, a better way to do this is just to put it in a namespace instead of a struct, because then members of a struct have internal linkage, members of a namespace have external linkage, so that's going to compile. Let's talk about auto a little bit. Auto is another one of those great features that we have since C++11 that make code shorter, better to read. And there's a lot of great use cases for auto. Like, for example, in the first line, so the first auto means we don't have to spell out the iterator type, right? So that's great, obviously. The second auto is something that we have since C++14, which is called generic lambdas, where you don't have to spell out the type of the argument of the lambda. So those are obviously great uses for auto, because it means shorter code. Now the second line is, I would say, that really depends on what you're doing. If you have a function that returns an object, you can write auto if you don't, basically either the type is obvious or it's not important what the type is for understanding the code around it. And then auto is fine. But sometimes you need to know the type, and then the person who was reading this code would have to look up the definition of that function to figure out what type that is. And if that happens, I would say we should not use auto. And then one other thing that I noticed is that people do things like that. So that, okay, that was supposed to appear. Again, this is the problem with the slides. But people do things like this, where, if they declare const, ints, or floats, or whatever, they also use auto. And I don't like that. I use the old-fashioned way, because I think in this case auto doesn't really add any information. It actually removes information. It makes it a little bit harder to see what's going on. You need to think a little, like those extra seconds more. It actually makes the code less readable. Now people say, hey, you should use auto, because then if you use auto, then you have to initialize the variable, right? So that's going to prevent you from having uninitialized variables. So that's great. My opinion is that, yes, that's great, but that's only going to help you if you have a rule, that you have to use auto everywhere. But at that point, you can also have another rule which just says, initialize your variables everywhere. There's this other opinion that, okay, sometimes you need to spell out the type to make it clearer, but then you should still use auto, and you should do it like, you should write the type on the right and use uniform initialization like this. And I think, yes, with objects, that's nice, but again, with ints and doubles and these fundamental types, that's just more typing and doesn't really add anything. And additionally, it has these other problems that with types like that consist of more than one word, like long double or unsigned int, this is not even going to compile. Like, for example, on Clang, you get this compilation error. So again, I would actually personally not use this. I would use the old style. So, but you can obviously do whatever you want. Lambdas. Now, lambdas are also one of those features that I really like. You can write those functions which take any type of function, like we want to call any type of function asynchronously. So that's great. You can pass it a lambda. You can capture this. You can call member function. And that's replacing a lot of really ugly features in C++98, like stdbind or stdmemphen, if you have ever used this stuff. I don't think it's really nice. I think lambdas are much better. And then also we can use them with STL algorithms, like this one, which is also really nice, as long as the lambda is short. Like this is, for example, good, because then you don't have to put the comparator. So here it's really obvious what happens here if you just stare at the code. You have items and you sort them by time, right? So you don't have to put this into like a comparator object somewhere else. It's all locally. It's all really nice. But I think if the lambda becomes longer than that, then actually sometimes it becomes less readable, because then maybe the thing that you're doing in the lambda is a bit more complicated than this. And then maybe actually it's doing something that's not obvious. Maybe there's some logic in there, so you should give it a name. So I'm personally not a big fan of lambdas that go over multiple lines. I think they should be functions that have names that tell you what they do. And also I find that nested lambdas tend to be quite unreadable. I mean, if this is essential to what you do, then by all means use them. But if it's not, then I would avoid that to just make the code nice and readable. Now, this is another example. What happens when people realize that they can use lambdas and STL algorithms? They start writing code like this example here at the top. This is something that I started seeing in code reviews a lot, where basically what this, so yeah, ignore the red line again. Like you're supposed to see the first half only. So this is just a function that that's actually That's actually production code. So that just takes a string and a value, and we have these dynamic variables. It's actually from our live coding IDE, this part of the code. So you have these like dynamic variables where you have some code running on the device, and then with a slider you can actually adjust the value, and it's gonna inject that value into the code that's running on the device. So we have these dynamic variables there, and they have names, and then you just want to find the one that has the right name and give it a new value, which is a simple task. Now you can use find if, and then you have to give it begin and end, and then you have to give it to lambda with the predicate, and then, okay, you have to decide how to do the capture. Now this person chose to capture the string by value. I'm not sure that's a good thing. Maybe, you know, that's another topic, and then you have to store the result in an iterator, and then you have to compare the iterator with end, and then you can decide whether you should do something. Now, I think this is over-engineering in this case because the task is so simple, and people actually do this a lot. And I think, you know, in this case, it's much more readable if you just write a good old loop, or actually even better if you write a range-based for loop. And if you just write it like this, the code not only becomes much shorter, it actually also becomes much closer to English. You can just look at it and it tells you what it does. You know, for, like, go through all the variables in metadata dynamic variables. If the variable name equals name, set the current value to new value and return. So it's really nice flow. Someone staring at this function can understand in 3 seconds what it does. Someone staring at the top, well, it's not particularly difficult, but it's definitely a bit more confusing maybe. Another thing that I noticed is, you know, we have std parents in C++11, we have std tuple, and they're useful sometimes, but actually I end up almost never using them and almost never recommending using them in application code, because if you have a pair, for example, of a string and an int, it doesn't tell you, so this type doesn't tell you what the string and the int means, right? And if you use an object of this type, it's the same, like you refer to them with first and second, or with the tuple you refer to them by like get 0, get 1, get 2. It doesn't tell you what this means. So most of the time I find it results in much more readable code if you, instead of doing this, you just create a custom struct and you give names to those things. So you say what the string and this int means. And this is probably going to compile down to the same thing anyway. And the code is much more readable. Now, one great feature about which we have in C++11 is brace initializers, and I think brace initializers are great to reduce the amount of code that you write, to get rid of duplication, and they have many different use cases. So, of course, there's this basic one where we have uniform initialization, where we can initialize containers with this syntax. That's much shorter than what you had to write before. Then you can use them if you pass arguments. Now, for example, here, let's say we have this struct, which is a point, it just has 2 numbers, and then we have a triangle, which consists of 3 points, and then the constructor of triangle takes 3 of those points. So now, you know, if you want to construct a triangle, you know, you don't have to repeat that type, maybe. And then, you know, if you just use brace initializer, it's going to become much shorter. Because you don't have to spell out the type. But now again, I would only do that if it makes the code more readable. Now in this case, for example, I would do that because I think it's really obvious in this case what happens. You know, we have a triangle and then it gets 3 points, and each point consists of, you know, an x and a y. So it's really obvious what's going on here. But maybe sometimes if you have an initializer list like this, it's not going to be obvious what the things mean, and then I would not use it. So this is always sort of like the thing that like how do we decide whether to use stuff like this? And the same passing arguments, the same of course with returning. You know, we know the return type of the function. It's actually the first thing in the function signature is the return type. So we don't have to spell it out. We can just omit it. That's really nice. But only if actually the resulting code is understandable. If you would have to look up some stuff to understand what those numbers mean, then I would not use that. Another use of brace initializers that I found really useful is these default member initializers. So in Juice, we have a lot of classes like this one, for example, where you have these different constructors, right? And then typically you have a default constructor which initializes it to some the things to some default value, and then you have some other constructors. And then, in C++11, instead of doing that, you can put them in a default member initializer. Now we had a discussion, what kind of like style we should choose, and then after a while it turned out that actually it's always a good idea to use these default member initializers, because this way, even if you omit the initialization in the constructor, they're always going to be initialized. So there's no way they're not going to be initialized. And then if you have more constructors, you can initialize them to something else, and this is still going to work, but you're never going to have anything uninitialized. And it also always results in code that is shorter if you use them, especially if you have many of these constructors. So it's shorter and safer. So I think it's always a good idea to use them. There's one problem though. If you rewind to C++ 98 days, one thing that was always working is if you have a really simple struct like this, it just has 2 numbers, and there's no constructors, nothing, and there's no private members, and there's no base class, and nothing like that. It's just like a simple pod. You can initialize it like that with this aggregate initializer. This the point 1 here, the first line. So that always used to work. That's the feature that comes from C, right? That was there for a long time. And of course, the problem is that if you default initialize it with the second line, then it's going to be initialized to garbage. So yeah, cool. I mean, how can we prevent that? In since C++11, we can stick the default member initializers in there. Now in C++11, there is a problem that as soon as you introduce this default member initializers, aggregate initialization is not going to work anymore, and you get this compiler error. So then, to get around this compiler error in C++11, you again would have to write your own custom constructors or with these initializer lists. But happily, in C++14, they fixed that. So actually now we can write these really compact pods with no constructors at all that we have to define. We can use default member initializers and it's all going to work. So this is really short, compact, readable code, and this is C++14 fix that I really like. Let me see where I am here. Oh yeah, one other thing that maybe not everyone is aware of is that you can also call functions in there. Just like you can call functions in the old school initializer lists. So that's also really great. Like for example, if for some reason your points need to have unique IDs, you would normally initialize them in the initializer list. And then again, if you have multiple constructors and you forget to do that for one of them, then your point is not going to have a unique ID, but then you can just stick it in the default member initializer, and then no matter how many different constructors you have, there's no way this is not going to get called. So one other thing is minimizing scope, right? If you have a variable like a local variable somewhere, you want the variable to be only in the scope where it's actually used. You don't want to leak it. You don't want it to leak like in the outer scope. So, for example, here, if you for some reason you want to print out the first 6 prime numbers, then you can create a list of the vector or even the C array of those numbers, and you can print it out. But actually, you only need it inside the loop. So what you can do with base initializers is you can just omit creating this object altogether and just stick the initializer list directly into the range-based for loop, and then it's only going to be in that scope, and you're actually not going to have this extra object at all. So that's also, again, much more compact, much more readable. On the other hand, if for some reason this particular list of numbers there has a meaning, like if this is a particular sequence of numbers that is somehow meaningful elsewhere in your code, I would of course not do that. I would probably create a static object and give it a name that describes what it does, and stick it somewhere, maybe in a header or wherever it fits in your code. Another example for minimizing scope is something that we have also in the juice coding guidelines. You know, a lot of the time you have something like this where you have a function that returns a pointer, and then you want to check if the pointer is null, and then if it's not null, you dereference it, you do something with it. Now, again, the pointer is sort of like you only need it inside this if, right? You don't want to use it if it's not null. You don't want to have access to this named object. So you only want it to live in that scope, but and you can do that by just putting the initialization inside the if. Now in C++ 11 and 14, this only works with the pointer, yeah, because a pointer or a smart pointer has this. It would also work with a unique pointer because you can convert it to bool implicitly, so that's also going to work. But that's only going to work with pointers. Now in C++ 17, we can do much more stuff with these definitions. So actually in C++ 17, what you can do is if you have an if, you can define any kind of variable you want, semicolon, and then you can do your condition. So this is a great thing in C++ 17 because it allows you to minimize the scope of the thing that you want to check and then use in many more use cases. For example, in this case, if you just look at this part of the slide for a second, let's say we want to insert something into a map, and then if we actually inserted it, then we want to, for example, if we didn't insert it because it was already there, then we want to, display an error. Now in C++ 11 and 14, what you have to do is insert returns a pair, right? So the first is a bool, which tells you, did you insert it or was it already in there? And the second one is a reference to the thing. So insert returns this pair of bool and reference. And then what you need to do is you need to do the insert. You have to store this pair in a result, and then you have to check the result dot second, which is this bool. Oh, actually, sorry, it's the other way around. The first one is the reference to the object, and the second one of the pair is this bool that tells you, did you insert it? So you need to then check the second of this pair, which is this bool. Did you actually insert it? And if no, then you can do something. And again, this result is sort of outside of the scope where you actually need it. You want it to be only inside this if. So what you can do in C++ 17 is you can initialize the result. You can initialize whatever you want. So we just initialize this pair, result equals map insert, semicolon, and then we can do the comparison. Right? So then it's only going to be inside this if. Now, again, I still think this is not ideal because you still have to handle this pair. That's just the way std map works. So in Juicy, you would just write it like this, map add if not already there. So it would be nice if std map had a function like that just returns the bool, but it doesn't. So it's still slightly unreadable, but less so than it was in C++ 14. Now, I already mentioned the C++ 17 feature, so let me just quickly mention a few others, which I think are maybe not sort of like not necessarily like the big features, but some little features that I think are really good for this kind of readability, making code more obvious, and stuff that's really easy to sort of explain as well to other people. And so I think these are great features that I'm really looking forward to actually use in production code. And some of them relate to variadic templates. Like, for example, this is a very simple example. You have a function, and it adds some objects or numbers together, and you want it to be variadic, and you can expand that to like more complicated actual use cases of variadic templates. So if you want to write a function like this in C++ 14, you would ignore the error for now. In C++ 14, you would have to write it with a variadic template like this. Right, where you have a first arg and you have the rest of the args, and you add them together, you have this parameter pack, and then you do this template recursion. And then the template recursion, of course, for this to work, you need the base case. So you have this, you need to define this base case which takes no arguments and does nothing just to stop the recursion. And that's just code that, so first of all, that's code that's just literally does nothing, so I don't think it should be there. But it has to be. And even then, if you do that, it still doesn't compile. Does anyone know why this doesn't compile? yeah, so there's this, there's this other thing, like, for some of these features, like, you have to know too much about, like, complicated C++ stuff to actually be able to use them or read them. And I'm sure that many of us in this room have no problem with this, but, in everyday life, not everyone knows these details. Like, for example, in this one, the C++ standard says that it actually depends if you have overloads like this or template specialization. Actually, it depends on the order in which you define them. So that's not going to compile. You have to do it the other way around. So that's going to be much nicer in C++ 17. So one thing that you can do is, for example, okay, so we want to get rid of this base case, right? So what we want to write is we want to write it like this. So we don't have the base case. We just say, okay, is the parameter pack empty? Right? This is the size of ... operator that tells you how many parameters you have. And if there's only one argument, if there's no extra arguments, then just, okay, so if there are extra arguments, then keep recursing. If there are no arguments, just return the one number that you have. So that's something that you want to write, because that's much simpler. You don't need the base case. Unfortunately, that's not going to compile in C++ 14, because if you have, let's say you have only one argument, so the if is actually false, right? So this line of code which triggers the error, you don't need it, because you are already in the case where you just want to return the one argument. And also it's like a compile time thing, so the if is false and the compiler knows that, but there's this requirement that it still has to, like, even if the if branch is never taken, and you know that on compile time, it still has to be code that compiles. So, and there's no sum with no arguments if you don't have this base case, so this is not going to compile. Now in C++ 17, we have a nice fix for that, where we can write if const expr. So instead of if, you just write if const expr, and what it does basically, well, it says, okay, if the condition is false at compile time, I don't even care what the code in the if is. It doesn't have to compile, I just ignore it. And this lets us write compile time code that is much more easy to read, because it follows this intuitive if-else syntax, and instead of doing template specializations and this kind of stuff, you can just write it like that, and that's going to work. And actually, if the thing that you're doing, if the recursive thing that you're doing is a mathematical operator like plus or multiply or any of the other mathematical operators in C++, we have something even nicer, because here the red stuff is still sort of like boilerplate that we don't really need. Right? It doesn't really tell us what we're doing. So we can get rid of all of that by using fold expressions. So that, I think, is a really great feature, because it's a new feature, but it's sort of obvious what it does, I think. It's going to be, try to explain, sphere, for example, to a junior developer. That's going to take you a while. But this, I think it's really obvious what it does. It's simple, it's easy to explain, it's much more readable, and this is the reason why I like this feature so much. It's really flexible. You can do a right fold, you can do a left fold. If you don't, so it's going to create you don't have to define the base case, but if you need a base case that does something, you can define your own base case as well. So that's really great. That's really useful. And one last thing I want to say about C++ 17 is, so there's a lot of things that people have been writing and saying about returning by value and passing by value, or const reference, and what you should do. I'm not going to repeat all of that now, but I just want to say that I really like returning objects by value, because it's much more readable. It's much more obvious what you're doing than if you have an in-op parameter, if you're doing something else. You just have an object, return it by value. It's really easy to read code, and I really like to write that. And like, for example, here, it's not a problem. And of course, it's not actually a problem, because if you return like a vector int or a vector of something else, or even another object by value, whether it's a temporary or whether it's actually a named object, we have copy elision in C++. Like every modern compiler, if not too much happens in between those lines, it's always going to optimize the whole thing away. And so we have return value optimization, we have named return value optimization. So the copy constructor or the move constructor of those things is never actually going to be called ever. Actually, that's interesting because there was this rule in C++, this as-if rule, that the optimizer is only allowed to do optimizations that don't change what your code is doing, right? But that's actually an exception to that rule. So the optimizer is allowed to throw out the copy constructor, the move, like the copy and the move, and it's just not going to do any of the stuff. It's going to do RVO. And even if the copy constructor has side effects, it's just not going to be called anyway. So it actually changes what your code is doing. But it's a good thing because you have RVO. Now the problem in C++ 14, or since like until C++ 14 is, let's say if you have a class that's not movable, then you can't write that. You can't return it by value like this because even though you know and the compiler knows and the optimizer knows that you're not going to copy this thing, you're not going to move this thing, probably like you're never going to use these constructors. But again, like with the if and the if const expr earlier, C++ 14 requires them to be there. And if you say, well, they're not there, then you're going to get a compiler error. And fortunately, in C++ 17, that has been fixed. So that's going to compile in C++ 17. It's called the guaranteed copy elision. And I think that's great because I think returning by value and using the RVO is something that contributes to better and more readable code. And this means that we can use it more often. There's more cases where we can actually make use of this feature. So that's a great thing. So this is, I think, all I have about C++ 17. Yeah, I have one more thing about something for the future, like concepts TS. So a lot of people are really excited about concepts for many different reasons. I'm excited about concepts because they get rid of another feature that I think is really, really unreadable, which is still enable if. So if you remember again this point class with the two numbers that we had earlier, and let's say you wanted, so the type of the number is the template parameter, it's the t, and let's say you wanted to have your point class in such a way that it only compiles if t is a floating point type. Now, until C++ 14, the only way to do this is to, and actually still in C++ 17, the only way to do this will be to use std enable if. There's different ways how we can use this, but one of the ways you can write it down is this way at the top there. And I find this is really, really ugly because I can never actually even remember how to write that exactly. Every time I have to look it up, even though I have used it many times, because somehow it's just like so hard to remember and it's so hard to write down. And if people haven't seen this before, they're going to look at this and they're going to be like, what is going on here? But then if we have concepts, we can write this much nicer. We can define a concept for floating point, and then the syntax is going to become like this. And this is much closer to English, and it's much closer to something that's readable and makes sense. So there's the current TS contains these three different ways to write this down. So there's this long way here, then there's a shorter notation, which is the second one, and then the TS also contains the the third syntax, which is at the bottom. Now, actually, the third one I don't like that so much because I think the first two are really readable and nice and really close to what people would expect that already know about templates. The third one, I think, it's not actually much shorter than the second one. It's a bit shorter, but it's more confusing. Like it doesn't contain the word template. It has these braces which look more like something else, like an initialization maybe. So I think this syntax is a bit more confusing. And also we don't need all these different syntaxes for the same thing. So I have this hope that actually this third syntax is going to disappear from the TS before it gets into the standard. But yeah, let's see about that. Yeah, that's all I have. Thanks. Also, the talk was in English, but I do speak some Russian, so I can accept questions in Russian or English, if you like.
Hello, thank you for the talk. I feel like that I will post the link to the recording of your talk in code reviews a lot since now. So thank you for that. First, I would like to comment on your first slide when you were discussing about erase remove from the vector and the proposal that we have. We can actually use the ready solution from Boost, which is called Boost remove erase if. So we don't have to wait for this proposal to be ready.
Yeah, I mean, some of the stuff is in Boost, and like the string replace is also in Boost. But for example, we don't use Boost, and I think in a lot of other companies, I would like to use Boost. There's technical reasons why we can't use Boost. So Boost is nice, but it's much nicer to have the stuff.
Yeah, but you already had example for Boost, so I thought that it would be consistent. And another remark about how to use Auto, and then different people use different IDEs, and most of you use some code review tools. And usually code review tools is not allowed to easily check the type or use capabilities of IDE for particular variables. So that was the comments. And the question is, do you have any tools to enforce that consistent coding standard that you developed?
Well, this is just stuff that sort of came up in code reviews that I did and some code that I wrote myself, and I just kept basically collecting all these things. So some people were like coming to me and saying, hey, there's this weird compiler error, can you check this out? So I just kept like a list of those things that came up, and basically those are the examples. So it's not more than that at this point, but I guess that it's an interesting question, because if you have access to something like the Clang tools, or if you're maybe developing your own IDE, or if you have like those guys that are developing this like static checker thing, if you have the machinery there, then it would be actually interesting to not just check for bugs, but actually enforce guidelines like this, or like good practices like this. And it also, I think, it goes a bit into the direction of the keynote this morning about the core guidelines, which is a lot more stuff, of course, than this, but it's also this kind of thing where, yeah, it would be great if you have a static analyzer that can actually detect that, and it's actually even better if you would have some kind of tool with like a syntax tree kind of thing, which just automatically refactors that. Some IDEs actually do that. So yeah, that would be absolutely great, and I'm sure tools like this will come up, or maybe they even already exist and I'm not aware of it. I know that, for example, the JetBrains stuff does some automatic refactoring, but I'm not sure how much of the sort of like newest C++ stuff they have in there, but I'm sure this is stuff that's going to come. So looking forward to that.
Thanks.
Thank you for the talk. I think concurrent code often becomes unreadable. Could you please share some experience with using lambdas or maybe coroutines to make, I think, code more readable? Thank you.
Okay, thanks for the question. I think that could be like a whole talk, basically, the answer to this question. Yeah, I don't know. So in Juice, we have our own like thread class and our own machinery for that. So I'm actually not using the like C++ concurrent stuff on a daily basis. But yeah, I'll have to think about that. Maybe we can have a chat after the talk, look at some code and discuss this further. I think it's interesting. I don't know what to say right now. It's quite a complicated topic, but let's discuss afterwards.
Okay, thank you.
I have a shorter question. It's about lambdas. So you said that you don't like lambdas more than one line, basically.
Yeah.
But what if
just my opinion.
You can just assign a lambda to local to the function object and use it with a name? Why not?
Yeah. Okay. Yeah. Obviously, you can do that. You can say auto, compare whatever equals lambda, and then you have a lambda in the object. But so I think if you do this, then it's better to do it as a sort of old school named function, because then it's going to be somewhere in a header maybe. It's going to be like, if you have a lambda and you put it into a variable, you can give it a name, so that's good. But it's going to be somewhere in your local scope, so it's going to be harder to find, unless it's like really, really close to the other code.
What if this code block logically needed only within this method? It's not needed anywhere else. Why would you put it in the class interface?
Okay. If you have so you're saying you have a lambda, and then immediately afterwards you use a lambda in an algorithm, and that's the only place you use it. Yeah, then I would do what you say. I would say auto, whatever the function does equals lambda, and then use it. And that is going to be the same amount of code if you stick the lambda inside the algorithm, but it's going to be less nested and more readable, and you're going to give it a name. It's going to tell the reader what it does.
Yeah, that's what I think.
Yeah, that's what I would do exactly,
Thanks.
but only in this case.
I have a question concerning your example of members initializer. Your example with the point class where you initialize its members in the place they are declared. Yeah.
This one?
Yes, this example.
Mm-hmm.
You encourage using this everywhere, but your talk is called Readable C++, and I think that this technique sometimes decreases readability, because when you have a constructor which initializes not every data member. So when you read this, for example, here the second constructor initializes only X, and the Y is not initialized. When you read this code during code review, you see that only one data member is initialized, and there's one more WTF during the code review, and then you have to go to header file and make sure that another member is also initialized. So this usually this technique is that doesn't always improve readability of your code, because now not all the members are initialized in the same place.
Okay, so thanks for the comment. So that also depends, of course, always on the code that you write. But so first of all, I think if you have a code review and then someone notices that you forgot to initialize something in the initializer list, that's already too late. If you do this, then this can never even happen, because everything will always be initialized anyway. So that's much safer. And the other thing is, so yes, I'm not sure why you're saying this is less readable, because it's done in one place, right? Like, for example, something that we do in Juice is that all these members and all these initializers are always at the very bottom of the class, so they're like really easy to find. But if you have like 10 different constructors, which in a library class that can easily happen, then it's much more difficult to read all these constructors and look at all these initializer lists and see if there's something dodgy in there. So it depends on the class you're writing, but I think actually in most cases this will be more readable.
Yes, but implementation of constructors is usually in a CPP file, and initialization of your members is in a header file. So you during code review, you have to switch between header file and source and CPP file to make sure that everything is initialized. Yes, I agree that if you initialize every data member near the declaration, then you just ensure that they all are initialized and you don't have any problems. So it's just, for me, not that obvious that this suggestion is always a way to do. It has its drawbacks.
Yeah, okay, but it's always shorter and it's always safer.
Yeah,
so I think these two are very strong arguments, and I think these arguments outweigh the other argument that you may have to juggle between two files.
Yeah, I think I agree. I agree. Thank you.
Unfortunately, the time for question is over,
Okay.
so we can proceed to dinner.
Yeah, we can chat afterwards, and you can also talk Russian to me. I can practice my Russian. That's going to be good. Thank you.